Yeah, let's go. All right. Thanks for coming. Thanks for getting out of bed. First, a small story. A long time ago, I was a child. I got a pocket knife for my birthday. And I loved that pocket knife for a while. I played with it and I did kid stuff with it. But at some point, there was a problem because my sister, who was a little bit older than me, she had a slightly bigger pocket knife and it had more gadgets. And the problem was that her pocket knife had a bottle opener, and mine didn't, and that really pissed me off. Not that I really wanted to open wine bottles, but that was kind of beside the point, and that's somehow always what happens with pocket knives. It can do a lot of things, and you always want more. And slowly, they get bigger. I would have loved to get this one, didn't get it. It's like 500 euros. But if you look at it, you don't really need to think hard to see that it's really bad at anything. I mean, anything it can do badly. Imagine turning a screw with that whole block of metal in your hand. It's gonna be horrible. Or chopping food with it and then trying to clean it somehow. It's terrible. It's kind of a symbolic piece of technology that's really about the theoretical ability to solve a problem and not so much about actually solving a problem, right? So every single part of that knife has a counterpart that costs a few cents and that's in every way better. So I'm not actually going to talk about pocket knives, I'm going to talk about us, because we tend to make a lot of pocket knives, things that can do a lot of different things that maybe should not be together. And for us, it usually starts all right, and then we have a good focus on what we want to build, but features come in, and slowly we have like more and more of a monster, and at some point it just gets a bit silly. So now, if we talk about databases, they have a very interesting history because storing data efficiently and reliably, we found out pretty early in our history that it was hard, and that you don't want to do it every time you build a new app that you want to rebuild the database. No, so those became big off-the-shelf products, huge flagship products of big companies that were extremely expensive, and like Oracle, DB2, like those. And those databases tried really hard to be the only database you will ever need. And because money. So at some point, they will start to add features like Oracle had some object store that was horrible, or some XML scheme storing, and because they just try to add more and more features, and it really doesn't make all that much sense. So at some point, it was really when the web scale started, it was obvious that one kind of database couldn't do everything, and that's when the whole NoSQL thing kind of exploded. And after that, you got a huge number of different kind of databases, but still, I still think that even with all the NoSQL, you can't do everything with one single database. So you need to have more. So today, I want to talk about embracing the multiple databases. So don't stop trying to do everything with one database. It's a habit we have from the past, I think, but we shouldn't. A little bit about me. I'm Frank Lyaruu. I'm CTO of a small company in Amsterdam called Dexels. One of our biggest clients is Sportlink, service provider for sports, for soccer, for volleyball, all kind of things. We have been around for a long time. It's close to 50 now, I think. We manage all the things sports associations and clubs do. We have a few million players. We have a few thousand clubs, about 40,000 matches every week. And we have a very spiky load, but we can predict it very well. So that works out usually. our technology stack used to be an Oracle database because that's what we had, some Java-based application servers, and a diverse set of clients. Looks something like this. We have seen millions of those. Nothing exciting there. So in practice, it's a little bit more like, a little bit messier than this, but something like this. So for the a few years back, we got a kind of a challenge because up until then, we always used to, the clubs would do pretty much everything. So if somebody changed address, the club would do that, or they planned all the matches, or make all the changes. And we want to stop doing that. We want to give every player the opportunity to change that. So that means that we would effectively go from 6,000 users to a few million users. And that would, that's not something you brush over easily. So we also knew that all right, you still there? Oh, what did I do? In my blind panic. Yeah, so we couldn't move away from Oracle in the short term, and scaling Oracle, if it's technically possible or not, I don't know, but we definitely knew we were not going to be able to pay for it. So we had to do something, right? So this was the plan. We have our old stack, which is pretty much the same as it was. We have some magical synchronization thing. And here we have another stack based on MongoDB. We had good experience with that. And that can serve all the traffic. So my initial thought was, shouldn't be too hard. So we had a plan, capture the data from the Oracle database in real time, dump it into Kafka to be able to queue all of it. And the other side, insert it into MongoDB, and then go on holiday or something. So that's never the way things go. But how familiar are you all with Kafka? Who knows Kafka? That's good enough for me. So Kafka, it's a platform now. It used to be like a broker that essentially you shove stuff in it and it comes out on the other side. Cutting some corners there. There are some other parts that are come more recently. Connect API, that's a standard API to get stuff into Kafka or out of Kafka. And the Streams API that will allow you to do stream processing on topics. And I'll get back to those two in a minute. Well, this is, well, we know that. So, change data capture. It's a pretty old field, but it has been remarkably bad until pretty recently. So basically what this means is that you point to a database and you get all the changes that are made in that database in real time. Ideally, you can also get some historic view of the data so you can get all the changes that have happened until then, or some compaction of that. That sounds like a pretty straightforward thing to me to have. It isn't. It isn't. And yeah, there's a nice quote of Martin Klepman, and I really like that because it said, "Why can't I do MySQL pipe Elasticsearch?" Straightforward thought to have, useful even. And I agree with him. I think databases are self-centered. They try to do everything for you. They don't play nice with other databases. They don't really think about, oh, how do I easily compose with other databases? No, they just try to be one database, and if you need to do more, you add the feature request and maybe even give them some money. But there is some hope. There is a feature that basically every database has, well, most of them. And it looks like they all came up with it independently somehow. And that's the write ahead log. And what that means is that if you make a change or an insert into a database, the first thing you do is you log that request that you want to make that change. Where once that has been saved to disk, then you actually use that log to change the data in the database. Because if you have that, if something goes wrong after you log that log, you can still replay that log later and fix the database if it crashes somehow. So it's a lot, because the actual changing data, if you change data on a disk and the database crashes at some point, it might be corrupted. So you need some kind of log, append-only log, to recover. So Oracle calls that archive log, MongoDB calls it the uplog, Postgres a write ahead log, and MySQL calls it the bin log. So another use of the write ahead log is replication. So with that write ahead log, you can make a master-slave replication. So the master takes all the updates, it writes it into its log, and it distributes its log to its followers. So they can build up the same data set, and if you query, you can query of all of those. Again, there is some eventual consistency there, so it's not completely trivial, but this is a pretty common setup as well. So what we wanted to do was follow that uplog and put it into Kafka. Pretty straightforward, but there is it's not as easy as it seems, and I want to because we're actually like using a sort of internal system that never really has been exposed as an API. It's not like if you have a SQL or some other query language that is clearly defined API. No, it's a kind of internal thing. Like you have to sort of dig down in the documentation or maybe even the code to figure out how it works. I think a good illustration of that is the documentation of Postgres. And it says from 9.4 on, they had something called logical decoding. And this page explains what it is, so that you have like you can extract the persistent changes in a coherent, easy to understand format which can be interpreted without the detailed knowledge of the database. And that says also something about the situation before this, the way they put it here. So it was an incoherent, hard to understand format that was impossible to understand without internal knowledge of the database, and that was definitely true. So kudos for Postgres to do that, but the other databases have a similar problem. So now here comes Debezium comes in. Who has heard of Debezium? More than I thought. It's from Red Hat. It's pretty young. It has been around for a few years, but now it starts to mature a little bit. It's basically, it tries to standardize that part of reading and write ahead log of different databases. So they're slowly adding more and more databases there. It's based on a research project called Bottled Water that basically they did that for Postgres, but they try to expand it to as many databases as possible. They support now Postgres, MySQL, and MongoDB. Oracle is in progress. So I don't know if there will be more in the future. It's one of those products that has a really dirty job. I mean, it's like at first I didn't know this was a thing, that it was hard. And once you have something like this and it works, you forget about it immediately because it works. And it doesn't have an UI, you just point it to a database and to a Kafka queue and it does its thing. So, if we make this a bit more concrete, we have SQL, the source database over there. It has It has a database, some application server, doesn't really matter. And there's a change, for example, some person, could be an update, could be an insert, doesn't really matter. And you put that into the Kafka queue. And on the other hand, we have a MongoDB database that listens to that change and inserts it into MongoDB. That is pretty straightforward. So it works, but there is a problem, and I guess most of you have figured that out, because this is not really diversity in itself, because we take a relational data model and drop it into in a document database. So it's not really relational anymore, because we're not in a relational database, we can't join, but it's also not really a document because, well, it's straight out of a relational database. So if you're not able to change the data model, you end up with the worst of two worlds, right? You have a data model that relies on joining and on that it's relational, and you have a database that cannot do that. So let's give an example. If you have like some basic model, some basic data model, you typically have something like, if you have different kind of communications associated with the person, you have one table of that, and you have some persons that are associated with it, and you join them over the person ID over there. Nothing spectacular, but in MongoDB, you would want to have something like this, right? That if you query that person, you get all of those, and not that you have to grab them one by one from different corners, because we can't join. So we want to have also for performance to have as few queries as possible. So you want to optimize that document, that you just get one document that contains everything we need. For that, we need stream processing. So stream processing is that we listen to a stream, in our case a Kafka topic, and we have in this case two streams of two different change feeds from database tables, and we transform them. So in this case we want to do a join, but a join on a stream is not that straightforward if you think about it, because there might be millions of people on one side coming in record, and the communications flowing from the other side, they will not be in the same order, right? So if a record shows up with the communication of a person you have never seen, well, that person might show up later or never. You don't know. So you have to store that for that when that person shows up, you can join it and make the document into MongoDB. And that part, that kind of adds up, because what Kafka Streams does is it has an internal database called RocksDB. You can also plug in other ones, but RocksDB is very popular because it's an in-process database, so it actually runs inside the stream processing, and so it has a really low latency. And that's important because basically every time a record comes in, you need to query, like, is there something that visited in the past that I need to join with? So everything needs to do several queries, and this is just one of them, right? This is basically one place where you join in your relational model is all that, and that adds up, because like in our system we had like 500 million rows of SQL data, and that ended up being 0.5 terabyte of Kafka data. Not that bad, but the RocksDB data, just to do the joins, is nearly as big, and it's building a complete replica from scratch takes many hours. So it is not trivial at all, even though that if we have the resulting database in MongoDB isn't all that big. It's not terrible. It's a lot smaller than these, because it's in a very expensive format. Another thing to take into consideration when you use stream processing with this is that it's different than building queries or something. Like if you are building some piece of software that queries a database, you change your software, you try again. Is it what you want? No, you change it, you try again. For stream processing, it's not that straightforward because there is so much data that if I have a running system, I can change the system and restart it and keep running. But then there's some data that it processed with the old code and some it processed with the new code. And that's a bit tricky because in some cases you can get away with it, but often you kind of need to start from scratch to be sure that that this all still makes sense. So then you need to what we call a generation. So you really run the whole thing again on the old data, and you can do it in parallel. The old one is still running and happy, but you can build a new one, but it's expensive. So for effective development, you need a test data, a good test data set that's not too huge. Also, a lot of times we found contaminated data, and that was contaminated years ago, and it was not a problem until now. For example, there was, due to some small typo or bug, I don't know, there was one soccer match that had like 10,000 people playing in it. Never happened, but it was in the database, and now the whole replication crashes because it tries to make a document that's just too big. And there are a lot of those small things, so be ready for that, because they might not have been a problem in the past, but this is the kind of moment when they emerge. So from this part, this went in production last June. It's behaved pretty well. It's still a learning curve. Kafka Streams was in a pretty rough state when we started. It's so much better now. So in that space, in that sense, we were a little bit early, but I'm still stand by our decision. Now I want to go into a little bit of architecture. I kind of tend to avoid that a little bit, but to go into the obvious microserver thing, because you got it, there's a problem I always had with microservices, and that's like, this is kind of the idea. Microservice, you have a thing, and it has a private store, nobody can know what it is, you have some code, doesn't matter, and you have an API. And this is great if you can get away with this. If you can separate the data in different stores so that every microservice really has its own data. And what I have seen over and over again is that conceptual different services do need the same data, only just not in the exact same way, but they do need it, and it's hard to really store it somewhere. So if I put it in a bit of a more concrete situation, so I have some classic applications, SQL databases, some code. We have some analytics tool to, I don't know, maybe some dashboard or something, and we have the regular UI. So conceptually, it would make sense to split those two into separate microservices. So we have our core service and we have our analytics service. So that would look something like this, right? So we are free to choose an analytics database that makes sense. We have the dashboard, we have separate services. Great, and it's also, I mean, it makes also sense because if you do analytics, it might be heavy queries and you don't really want to disturb the SQL databases there. But this part, how is this supposed to work? I mean, it depends, of course, on the exact use case, but generally, if you have analytics, it really kind of wants all the data. It doesn't really want to store everything, or it maybe just wants to do some aggregations on it, but it needs a lot of it. So it's hard to make an efficient API that will not simply just copy the entire database. because that would completely defeat the purpose here. So for that, we have a thing called event-driven microservices, and that's basically what we are building now. Services, they push events onto a queue, and in this case, they do that by simply making changes in the database and let the change capture do that. And if you are interested in a certain piece of data, you can listen to certain topics, and you can materialize your own database if you want. So usually it has some kind of pub/sub, Kafka kind of thing. So it looks like this. We have our application, SQL databases, like we had before. You make your changes, and the analytics just listen to the changes, and they populate their own analytics database. And that's a much nicer way to integrate. Also, because if you for some reason you mess up your analytics database, if you use a thing like Kafka, you can ask Kafka to resend all the old data. So you can rewind basically and see all the old stuff again. So if you mess up your database here, your analytics database, you can say, okay, I'll throw it away, I rebuild it. And the core service will never, what happened here? Will never even notice, because you don't need to ask it that service. You can ask it to the event bus. So that makes it a lot easier to develop, and it makes it a lot safer to experiment. Event sourcing. So if you are a very brave man or woman, you can take that system we built, the one before, and you can actually, and this was not a good idea, you can actually kind of remove the source database, because if you capture all the changes, you can materialize any database you want down the stream, but that original one isn't really necessary anymore, conceptually. That does mean that your real important source of truth is now Kafka. It's a bit of a question if you should want to do that, but it is an interesting way of thinking. I think I personally have no plan to try it, but it's I think it helps you. It helps you thinking that if you think purely in terms of changes and not so much stateful data, because you can do a lot with that. And even if you leave that original database in place, what I think, if you have an old system like pretty much everybody will do, and should do in my opinion, it does open up, it gives you a lot of options. Well, because now we have this system, we can do fun things with it, because we have a stream of every change. We can listen to it and materialize out of the database without anybody else really noticing. So the risk is very low. So I'll give some examples of things we can do. For example, Elasticsearch. Everybody knows Elasticsearch, right? Yeah. So it's like a search indexer. So if you take a big data model with all kinds of tables and everything, and you dump it into Elasticsearch, you can offload a lot of the search load from your source database. Because, for example, if I have a SQL database and I want to find somebody, and I know a first name and a city or something, that's not something that SQL databases particularly like, that kind of queries. And in order to do all of those, you need to have a lot of indexes. Indexes slow down your write throughput. So if you can put a searching somewhere else, it can offload your database a lot. And you basically put the searching in a cheaper place. Because if your search is behind a few seconds, Nobody will really care. You don't really need to bother your transactional database with this. Also, I have seen that modern users kind of expect Google anywhere. So if you have an application and you have some search thing, you just want to type something in, press enter, and that thing knows what it is, what you mean. And something like SQL is just not really suitable for that, because it really expects you to know what you are asking for exactly. So another one, Neo4j. Any graphistas here? There he is. Yeah, so graph databases are really interesting things. I think if you would use it as your central database in a big application, it will make you pretty unhappy. But the way of thinking is really amazing, and there are some things that are completely horrible in pretty much any other database to query. If you, because it's a graph database, so if you visualize your data as a graph, and essentially the difference between a graph database and a relational database is that in a relational database, the relation is between tables. In a graph database, it's between rows, nodes. So some things that are really horribly complicated to do in SQL and pretty much any other database are so elegant in Neo4j. And if you can pretty easily materialize a graph database in some corner of your application, why wouldn't you? And it really simplifies some problems. And even, just the fact that you introduce a new way of looking at your existing data adds a lot. So another example, Firebase, real-time database. Who knows it? A handful. So essentially, Firebase is like is by Google. It's like a big JSON document in the sky. You can, it's hierarchical, so you can change certain nodes. Not only can you change certain nodes, you can register for updates on a certain node. So there are some really nice SDKs for web and for mobile that you can say, I want to display the value of this little piece of the JSON document on my web page or on my mobile app, and when it changes, it will handle all the updating. So it actually does it does a lot, and it makes, for example, publishing things, like for us it's interesting for if there's somebody interested in scores or something, you want to put it on some scoreboard or next to the field, and you just listen to the updates in Firebase, and then we don't even get the traffic anymore. And if you would do it in a more traditional way, you would have to pull it or something. Also, we can kind of loosen how we define what the database is, and also use this system to push data to caches. So we can, because we know when something changes, we can just use that to invalidate caches, and beside that, we can basically cache forever until we know there's a change, and that makes it very efficient also to flush. Even further, we can actually push data to clients. It's pretty much like the real-time database, but sort of homemade. But it's a so much more powerful way of using data that you don't have to query it all the time. You just push the changes. So, so my point is somehow that that databases are better as a team. It used to be a time that it was completely not feasible to have multiple databases, and that it was so much, the overhead was so much more than it would gain, but I think that time is over. I think it's easier now to use several databases, each exactly what it's good at, instead of one big one and try to make it do everything. That's just getting painful, and there is so much possibility we have now to we have so much more possibilities. And also I think it's very good for your development, because you can easily use new database, and it helps you thinking about data in a new way. And if you just keep plodding on your old database, you kind of stuck. So I want to try a little bit of a demo. It's probably going to fail. So it's not very visual. So I'll start with explaining what I'm doing here. I have balanced some containers on top of my MacBook. So it's a Postgres database. We have Zookeeper, Kafka needs that. We have Kafka. We have Kafka Connect with Debezium that takes the changes from Postgres and puts them into Kafka. We have Kafka Streams that will read the topics and reformat them, and we have a MongoDB as well. So we have a little bit of a demo database. Nothing particularly interesting here, but the ones we will be looking for is the customers there, and the addresses which have a one-to-many relation. Yeah, so this is the data model in Postgres, and we want it to be something like this in MongoDB, so we can do it in a single document. So let me try for a moment. All right. Let's see if this works. I hope everything's up. The most important part is that the IP address didn't change since I set up. And that's something we will find out, I guess. So this is the data model. I'll change this piece of data from Alabama to Texas or something. And here we see we are listening to the update queue in Kafka. So the change was picked up by Debezium and put into Kafka. I know it's not like a visually dazzling, but it's, if you fought enough for it, it's pretty miraculous. Another one. So after that, the streams processing kicks in, and that listens to the topic and will join it and make the join topic. So I will try to see if that still works. I change something again. I don't know. And there we are. And now it's a bit of an odd format, but you see that you have the primary message, and you have a sub-message there that contains the address with Iowa in it. And so this you can easily insert into MongoDB, and then you are pretty much in business for this small case. Oh wait, I need to turn off the mirroring. Yeah, so that's basically what happened. Postgres, the Debezium basically pulls them from Postgres, puts them into Kafka, takes it through streams to join them, and Kafka Connect also picks up the changes from Kafka and insert them into MongoDB. Demo. This is like, I think, one of the worst cliches in our business. It's everywhere. It's right up there with, oh, we don't want to reinvent the wheel. But I think what's worse with this one is that, in my opinion, it's used wrong. It's used usually when, oh, if you have some shiny new hip toy, you want to do everything with it. And that's, of course, a bad idea. But I think there is a deeper point here, that if you are holding a hammer, that hammer influences your thinking. The tool you're using influences how you are thinking. And that makes it pretty scary, because usually you think that you are the one in charge if you're holding a hammer. But maybe that's not completely the case. And so if all you have is SQL, and I know a lot of people like that, they are complete wizards with SQL, and they can make anything work. And that's true, and that will continue to be true. But that's kind of beside the point. We are smart people, we can make anything work. Doesn't make it a good idea. So I would like to invite you to try to you will always think relational. So you always believe there's something else. So I would like to invite you to self-examine a little bit how much our tools are influencing our own thinking, because there might be a lot more out there. And I think today I have shown some ways to, with relatively low impact, because we can ways to expand our thinking. Because, as I said, implementing this is relatively low impact, because your whole original stack is still there. It didn't change. The only thing you connected is the Debezium tool to your database, and you catch the changes, and then you can start playing with it. So I would like to invite to be a bit open-minded to examine new things, because even if you don't really end up using it, it will make you a more interesting person, I think. So with that, that's all I have. Questions? Right there. No, we don't. No, that would be a really bad idea. I tried. Now, we are moving as well as this. We are moving from Oracle some parts to Postgres, not all of it, but some of it. And also at the place where we couldn't get away with it, we use triggers to insert it straight into Kafka and bypass the Debezium. But yeah, Oracle is pretty sketchy at this point still, but they're working on it, and I have no doubt that in a few months or years, it will. Yeah, you never know. We've all been there. It will be very useful. Good point. Anything else? Oh, there. Oh. Yeah. Mm-hmm. Well, I mean, I am no lawyer, so I don't know what counts as removing. If I remove data from my database, it will propagate through Kafka. Kafka will compact that data and essentially remove it from Kafka. It might take a long time before it actually does that. So I don't know if that's good enough. But yeah, I do see your point in the sense that the more places you put your data, the bigger the issue is going to be. And yeah, I don't really have an answer for that. I don't know. Anything else? Right there. Well, our change load is not that enormous. It peaks at maybe 500-600 changes per second. So so that wasn't really all that exciting for us. But we have a lot of reads. So yeah, so we did not expect any problem. But even though, I mean, if we do big things like you just change 1 million rows at the same time, it handles fine. I mean, it will lag behind a little bit for a while, and then it will catch up. So if you are not critical in the sense that your data needs to be up to date in 1 or 2 seconds, then you can basically do everything you want. Right there. Yeah. So usually, if you mess up your read-only database, then you can start that from Kafka. So Kafka all has the relevant data. It does something called compaction. So it will, if you update the same record over and over again, it might delete the older ones because it's not critical for rebuilding it. But you basically tell it to reload Kafka and do all the. Maybe you need to do the event processing, the stream processing as well. That depends on your case, what exactly went wrong. But if it's just your database, you just need to replay the assembled code, assembled data, and then you're in business. And that's in MongoDB. That's really quick. Anything else? Then thank you, and see you around.